Okay, in this video I'm going to illustrate how to carry out a confirmatory factor analysis using the SIMPLIS command language in the LISREL program. So to do this, to utilize syntax directly and not focusing on importing data, but using existing matrix data such as a correlation matrix or covariance matrix and so forth, what we can do is we can go to File, New, and SIMPLIS project. So I'm going to give my project a name. So I'm just going to call it CFA EX2A, and then click on Save, and this interface will open up right here. So I've already had a little bit of practice with running this particular example, so I'm just going to actually paste in the syntax that I've been using to develop this particular video. And so as you can see, the first line is actually the title line. You don't actually have to have the word title in there. I'm just using that as a descriptor, and so I'm just basically titling this confirmatory factor analysis. The second line contains observed variables, and then you can see that I've got SE1, SE2, SE3, EFF1, EFF2, EFF3, and EFF4. And these are, for this particular illustration, these are basically items from a 7-item scale that was designed to measure self-esteem and self-efficacy. So I have items 1 through 3 representing self-esteem, and items, the last 4 items representing efficacy. So you have to specify your observed or your indicator variables. And then you specify the correlation matrix, and the correlations when they are entered is going to be they're going to be entered in the same order as what you have for your observed variables. So the one that you see on the primary diagonal, and really all the along the primary diagonal, that's just the standardized variance of each of these indicator variables. So for a standardized variable, the variance is 1, so hence the ones. On the off diagonal are the intercorrelations among the measured variables. So the correlation between self-esteem 1 and self-esteem 2 is 0.618. Between 1 and 3 is 0.725. Between self-esteem 1 and efficacy 4 is 0.135. Correlation between efficacy 3 and efficacy 4 is 0.594. So this is just basically a matrix of correlations that reflect the associations among our measured variables. The next line, I've included standard deviations, and you don't actually have to include this particular line. But if you want information in terms of with respect to an unstandardized solution as well as a standardized factor solution, then you might incorporate this line right here that would include the standard deviations for each of our observed variables. So the standard deviation for SE1 is 2.437, for SE2 is 2.372, for SE3 is 2.411. So that's how we can look at this. I also want to make one other point. I have the correlation matrix nicely kind of laid out right here. It looks pretty, kind of pretty clean, or more aesthetically pleasing, if you will. But you don't actually have to have it perfect in this kind of way for the analysis to run. So if you were off center or whatever, it's not going to make really any difference in terms of what is run. But I generally like to kind of keep it a little cleaner looking. Okay, so the next line after standard deviations is latent variables, and so here you're going to give the names of the variables that are theorized to impact the variation in the measured variables as well as the covariation among them. So I have 2 latent variables. I have self-esteem or esteem, and I have efficacy. So basically, esteem is assumed to explain the patterns of association among these variables right here, and the efficacy variable is being used to explain the pattern of association among those variables. So the next line then is relationships, and then following that, we lay out our equations. So I have SE1, SE2, and SE3 equals esteem. So esteem, because it is basically, we're assuming it is accounting for the variances and covariances among these measured variables, then esteem falls on the right side of the equal sign. So it's kind of like an independent variable. And so the self-esteem observed variables are falling on the left side, which are basically outcome variables. For the next line, we have FC1, FC2, and FC3 equals the FC latent variable. So here's our latent variable right here. So the point is that the latent variable would appear on the right side of the equal sign, and the observed indicators that are related to the latent variable will fall on the left side. And this is following the relationships command. For the next line, we have sample size, and so you do have to specify your sample size. Here I have it specified as 200. Keep in mind that it's possible that you might be running matrix data based on correlations and standard deviations and so forth that are published in an existing journal article or whatever. So you might be sure that you consider the sample size, obviously, in the journal article. If you don't have sample size, it's not going to run. So be sure that you consider that. The next line is I'm just asking for residuals, and then finally a path diagram, and then you end it with end of problem. Okay, so at this point, what we'll do is we'll highlight everything. Actually, I'm going to save it. We're going to highlight everything and then click on the little LISREL run guy, and now we have our model. So you can see in the output file, the graphical output file, we have all of our measured variables, which are essentially being treated as outcomes of the latent variables. So the arrows are reflecting the fact that the latent variables are essentially predicting or accounting for variation in each of the measured variables. So if you look under estimates, you'll see that these are essentially unstandardized factor loadings. You can see right here, we've got our latent variables. This is basically the correlation between our two latent variables. So the correlation between esteem and efficacy in our model was 0.35. But again, the paths themselves are unstandardized path coefficients, or unstandardized factor loadings, excuse me. And over here, these arrows are reflecting uniquenesses, or basically variation that is unique to each of the indicator variables that is not being explained by the latent variable that is predicting. So at any rate, we also have, we have our chi-square test down at the bottom and root mean square error of approximation. And so in general, the idea is that what we're seeking is a non-significant chi-square value. In this case, it is statistically significant. Non-significant chi-square value would signal that our model has pretty reasonable fit to the data. The downside of the chi-square test is that it is affected by sample size, and given that SEM is a large sample technique, we can have somewhat modest departures from close fit, and it'd still be statistically significant. So that's one of the reasons why we look at various fit statistics in addition to the chi-square test. So the root mean square error of approximation, we're looking for values that are um, essentially below 0.08. More optimal values. The closer the values are to 0, the better the fit. And so values under 0.05 would be considered, close fit. Values up to about 0.08 would be considered reasonable or adequate fit. So at any rate, we can also look. So if we look at the t values here, you can see that. So these are basically t. Well, obviously t values, and none of them are red. If you have a red path with the t value, that indicates that that path is not statistically significant at the 0.05 level. So as you can see right here, all of our factor loadings are statistically significant. So that's actually good. That indicates that we've got reasonable specification of the indicator variables onto their respective factors. If we look at the standardized solution, click on that. Now you can see that we have these are basically interpreted as correlations between each of the indicator variables and their latent variables. So this is these are basically akin to the structure matrix when you're running exploratory factor analysis. Now it gets a little bit trickier or dicier if you specify a complex factor loadings where you have a measured variable loading onto more than one latent factor, particularly if the factors are correlated. But in this case, because we specified each indicator variable as loading onto a single latent variable, then these are essentially interpreted as in the way that you would structure a matrix. So we'll click through this and go to the our output file here and our text file. And so as you can see, you've got we'll scroll down and you can see that you've got the measurement equations here. You've got so these are the unstandardized factor loadings that I was telling you about. And you've got the standard errors, and then you've got z values that are printed out here. So, and then a p-value associated with with each test. So basically, once again, we're essentially looking for z values that are most of the time, and basically when you're talking about really large sample sizes, we're looking for z values that would be either above 1.96 or below negative 1.96. And the p-value that's printed out here, you can see that that esteem was a significant predictor of this SE1 item. So in other words, SE1 is loading onto esteem significantly. SE2 is also loading onto esteem significantly. SE3 the same, and really all of our indicator variables are loading onto the latent factors. You'll see also you've got R-square values, and this is just the proportion of variation in your indicator variable that is being accounted for by the latent factor. So esteem accounts for approximately 74.2% of the variation in SE1. It accounts for about 53.9% of the variation in SE2, and so forth. So we'll scroll down, and as you can see, we've got a number of goodness of fit statistics. So you can see that that basically we've got our maximum likelihood ratio chi-square. That's what was printed out on that original graphic. You also have an ADF chi-square as well. But as we look, we've got the root mean square error of approximation. Again, this was originally printed out on our for our diagram. And then we also have, kind of scrolling down, we've got the normed fit index, which generally ranges between 0 and 1. It can be a little bit higher than 1, but we generally would interpret that as 1. We've got the non-normed fit index, which is referred to as the Tucker-Lewis index, or also referred to as Tucker-Lewis index. and the comparative fit index, or CFI. And so what we're looking for these indices right here are values at a minimum that would be above 0.90, preferably above 0.95. And so you can see that none of these really kind of meets those thresholds in any kind of substantial sense, so or at all. So so those are kind of indicating that we have some lack of fit. The RMSEA, which I was telling you about earlier, again, we're looking for values at a minimum below 0.08, and we have a value that's 0.198, which is also indicating a lack of fit of our model to the data. Then we have the standardized root mean residual. We're looking for values that are below 0.05. Here it's a little bit higher than 0.05. We can also look at the goodness of fit index and adjusted goodness of fit index. Again, we're looking for values above 0.90, and so really just overall our model is not exhibiting a very strong fit to the data, at least in terms of the global fit statistics, even though our test of the factor loadings seem to be indicating that we have reasonable fit. So kind of scrolling down, you can see that we've got a matrix of standardized residuals. This is where that command for parent residuals comes into play. And so we're looking for, optimally the residuals would be closer to 0. So wherever you have values that are departing from 0, then you have some areas of potential misspecification in your model. So I'm not going to go into that too much right now, but I will also note that LISREL also prints out modification indices with the basic idea that you might be interested in, if the fit of your data is not as strong as you had expected or whatever, you might go into sort of an exploratory mode and try to explore possible respecifications in order to improve model fit. The downside of modification indices is that it's a purely empirical strategy, and so you can find yourself respecifying based on the fit statistic, or excuse me, the modification indices that may not replicate in other samples. So that's the downside. And a second downside is that you can easily find yourself making modifications to your model that don't really comport with theory. So it's important that you keep in mind that when you use it, when you use these types of indices, that you do it thoughtfully rather than just simply looking at it. But you can see right here that it gives you basic ideas as to where you might respecify the model. So like right here, you can see that you've got a path to SE1 from efficacy. So and it's giving you an idea about how much of a decrease in the chi-square value you would have. And basically, the smaller the chi-square value, the greater the fit of your model. So this is giving you an idea about how much improvement in fit you might have. Down here, it's got suggestions about adding covariances between your observed indicator variables and the possible impact on the chi-square values as well. So what we'll do now is I'm just going to not heed my advice on the modification indices, just as a way of giving you some further indication or further illustrations of CFA models using SIMPLIS. So we also have, let's say we have, let's say we want to we want to add efficacy as a predictor of SE1. What I could do in this particular case is I can leave all these the same way, but just add SE1 as an additional predictor. And so in this particular case right here, when I do this, you can see now I have a more complex factor model where basically part of the variation in SE1 is is it being accounted for by esteem, and part of it by efficacy. And you can see this is a standardized solution. So clearly, when you compare the factor loadings, SE1 is loading much higher on esteem than it is efficacy. If we look at the unstandardized factor loadings, this is it right here. And if we look at the t values, let's just take a look. Okay, so it actually turns out that efficacy is still a significant predictor of the variation in SE1. So conceivably, that might be worth modifying the model if there was a good theoretical rationale for leaving this factor loading in. When we look at the chi-square value, it's still statistically significant. RMSEA is also well above acceptable thresholds. You can see that now when we've added in this particular path right here, the relationship between these two latent variables actually decreases. And I also want to point out too, previously when we were talking about the factor loadings, I was using the term structure matrix, and now in this particular case, when we look at the relationship between efficacy and SE1 and esteem and SE1, now we have to look at these as kind of akin to partial regression coefficients, because we're basically looking at the relationship between each of our latent variables and this measured variable while controlling for the other one, because these latent variables are intercorrelated. So now we can look, let's just take a quick look at the output. So now you got SE1 being predicted by both esteem and efficacy, and so you can see that we have statistical significance at the 0.05 level for both of those factors. And when we scroll down and we just kind of take a look at these various fit statistics, the RMSEA value is still, like I said, is still above 0.05 and definitely above 0.08. So it's definitely indicating poor fit. We have a slight improvement in fit for the NFI, but the NNFI is still below what would be generally considered acceptable. The CFI is 0.92, so it actually increased a shade as well. The standardized root mean residual is below 0.05, which would be considered good, and the goodness of fit index is reasonable as well. But the adjusted goodness of fit index, which actually corrects for lack of parsimony, if you will, it's still pretty low. So overall, I would still not be particularly happy with this particular model. So let's just kind of look once again. Let's just see. I want to see what modification might produce the biggest bang for your buck in terms of adding an error covariance, so that you can see what that looks like. So we'll add in an error covariance between EFF3 and SE3. So in this particular case, if I wanted to add in an error covariance, what I can do is I can say set covariance between SE3 and EFF3 free. So basically, previously, actually I should have said set error covariance between, covariance between those three. So in this particular case, when we run the analysis, now we're allowing the uniquenesses or the error variances for these two variables to covary. So, and that's one of the nice things as you run CFA models, is that you can account for complex factor loadings, and you can also or factor solutions, as well as address possible intercorrelations among the error variances associated with your indicator variables. you have to sort of think about why you might incorporate that, though, other than just, like I said, just looking at the modification index. It could be, for instance, that maybe SE3 and EFF3 are worded very similarly. So there might be some type of method effect that may be producing the correlation that you see in the errors between those two variables. It's any number of possibilities. So just kind of looking at the unstandardized estimates, the t-values, you can see it's actually statistically significant. So there may be some other factor that is extraneous to the model that is producing correlated errors between these two indicator variables. So, kind of looking back at our output, then you can see that we've got basically everything is specified in exactly the same way. Down here you can see the error covariance has been added. So this is the error covariance at standard error, and then the z-value. So kind of scrolling down again, you can see the RMSEA just still is not indicating a good fitting model. The NFI and the NNFI are both indicating a good fitting model. The CFI is indicating a good fitting model as well. The SRMR is pretty good. Goodness of fit's doing pretty well, but the adjusted is still not indicating a great fit. So we have some fairly mixed evidence here of the fit of the model. RMSEA tends to be one of the more preferred indices, so that one tends to be given a little bit more weight in terms of judging model fit than some of the others. So at any rate, like I said, this was mainly just to kind of give you a flavor of how to use SIMPLIS in order to carry out a confirmatory factor analysis in LISREL. Probably most of the time when you're running research, you're going to import a raw data set into LISREL and run your analysis from that. You can do pre-processing of your data set in the pre-list program, or you could do additional pre-processing in other statistical packages. But basically, like I said, this was just mainly to focus on the syntax structure.